So let's continue. The part of this lecture section is from the, actually should have been done before the break, but I didn't fit it in. So a different way of segmenting these images is to use something called quad trees. It's a kind of splitting the image into sub-images and checking the image properties in it. And if we start with an image like this, we do a split in 4 pieces. And in the different regions, you can see that there is a great variation within this one, no variation at all in this one, also variations in this and this. This means this one, we don't split in the next iteration, but the other 3 we will split. So again, we split them into 4 new subsections. And here you can now see that these have no variations, and the other ones still have some variations, so we need to split them again. And then you can continue like this until you reach a minimal region size that you specify. Smallest would be a single pixel. Usually, I think you should stop a little bit earlier. And in the end, you can see here that you have a more and more fine-grained level of detail around the edge. And the more complicated the edge you have, the more splitting you do. An example of that is on this image here, where we have a grasshopper, a radiograph of a grasshopper. And in some regions, you can see here, you have larger open areas, but the closer you get to the, in particular to the boundary of the grasshopper, the more detailed these quads, these regions are. So this is a quick, relatively quick way of splitting down the image. And it doesn't actually care about single thresholds because it's looking actually at the local variations instead of having a single threshold. Another way, which is taking this one step further, is to work with something called superpixels, and that is a more flexible kind of regions. And depending on what you say, which size of superpixel you want to use, sometimes you can work with this very large blocks where you allow a little bit greater variations, or you can go into finer regions, and then you can less variations, and then you have finer superpixels. And that can be used in the case of segmentation. We have an example here where we want to segment rock, clay, and pores. And in this example, just putting the thresholds like this. Now the color map is not perfectly matching between this one and that one, but you can see that you have these large grains. They are segmented relatively well, but you have also a lot of misclassifications or uncertainties in this image. And with the help of these superpixels, you can block up the image in larger regions, and then given each region, you can say what the statistics are, and then you can also assign better the classes to them. What you see here is actually that close to the edge, there's more happening, and then also these regions are getting very thin, and then we get this film effect that I mentioned before in the multi-class segmentation. And now in the break, I got a question about this film effect, and the question was actually, when do you know that you have a virtual film or a real film? And that is actually a question you have to ask yourself critically. Do you expect a film here or not? Is this something that is really happening, or should you get rid of it? And in some cases, it's obvious there shouldn't be a film. In other cases, well, then you have to really think about, is it or is it not? Can it be verified with other means? And if then you can see that there should be a film, then of course you have to segment for the film. But very often, this is more a segmentation artifact. I've seen horrible examples of someone in cultural heritage used extreme color maps, and with these color maps, they saw that there was some kind of coating on a mummy or something like that, and it wasn't true. It was just a color map artifact. So be careful when you see this kind of thin layers around the object, in particular when you do multi-phase segmentation. And here is what happened when we merge blocks of superpixels. So this is a reduction phase in the segmentation. And you can see here that we could have something like this. Looks relatively realistic, but still you have maybe some ISO lines that maybe not make sense. In this dark case, it's not so easy to see. So here I added some more joyful color coding, and then you can see also a little bit better these color effects along the edges. Then you can, of course, also go on doing the segmentation using superpixels, saying what region belongs to what. The color coding is maybe not ideal because this region here is not even looking like intensity-wise this one. So then again, it's the question about choosing the right color map for the purpose. So I'm skipping this summary so we can jump on to the supervised segmentation instead. And going on, until now, everything has been unsupervised. We didn't provide any information telling our segmentation what it should expect. In the supervised segmentation, then you actually start training your segmentation method in some sense. And we have some reading material. There is a lot of information about, so you have Introduction to Machine Learning, that's an ETH course. And then introducing decision forests, UNet, which is a convolutional neural network. And there you can get more background information about these methods that I'm going to talk about. There's a lot of modules to load. And there are a lot of supervised methods that we can work with. We can work with classification, we can do regression, we can do a combination of them. And then there is also the training phase that we need to train a model with known data in order to do later a prediction. And for the training, we need a ground truth. So then we come back to lecture 2 about having the right data for your purpose. And the first part is classification. And here we come back again to create the blob data. So here we have blob data. We have created 3 classes, and these will be used now to train different models. And the first one is the nearest neighbor, or k-nearest neighbor, kind of related to the k-means. But in this case, we are talking about classifying based on what you see. So if you have these 3 hikers, they look at the trees they see, and this says, okay, I see only spruce trees, so this must be a spruce forest. The next one, he sees a mix of birch and spruce, so he says this is a mixed forest. And so he says this is a birch forest. And that depends on what kind of, how many trees he looks at for making this decision. So in this case, you can see that he can look at 1 up to 4 trees. This one depends on, if he looks at only 1 tree, it could be that he's closer to the spruce. But if he looks at 2 trees, then he's already having a double decision. 2 trees to base the decision and saying it's mixed. This one, if he looks at up to 4 trees, he would say that it's a pure birch forest. And then if he would look at more than that, he would say it's a mixed forest. So that is the idea behind the k nearest neighbor, that you look at the closest objects, closest observations to your measurement point. And based on those, you decide what it is you want to see, what it is you see. So looking at our blobs, if we have different points, so I have point A, B, and C. Point A is a hard one, but I would guess it's closer to the yellow class. Point C is clearly in the middle of a lot of green ones, so that would belong to the green class. And the orange is a little bit question how many neighbors you are looking at. Could be that if you're looking at 1 neighbor, you will say it's green. If you look at 3 neighbors, you will say this one, yeah, belongs to the purple, I think it is, class. With this one, if you look at only 1 neighbor, you would say it belongs to the yellow one. If you look at 2 neighbors, or actually 3 neighbors, then you would say, well, it actually belongs to the green one. Yeah, I think, no, that's a question, which is closer. But I think, no, I think it's in general, it will land up in the yellow one, because the more pixels you add. So those are the different cases to look at. And if we now look at some training using k-neighbors classification, then I have 2 vectors. You have a value, 1, 2, 3, 4, and some classes, I am a dog. And if you now train this classifier, you associate these labels with the numbers. And if we do the training, it comes out like this. I have the output as this little list here. And if we test here now with different predictions, you have a 1.5 looking at the nearest neighbor. 1.5 should be in between M and A. And it seems like it rounds down. So it says that it is M. If you set input 100, which is way beyond the 3 that we had in the training, the 3 is still closest. So that will turn into a dog. And now we train our blob data again. We have X and Y positions, and we have group IDs, 0, 1, 2. And that is put into the k-nearest neighbors training model, where we train it. We have, we set up the classifier with only 1 neighbor, and we train it with class fit. And then we see what happens. If we would scan all points in our coordinate system, you would get something like this, that all these points here, they would be classified as yellow. All these points, here is a bit fuzzy, they are classified as the purple, and all these regions are classified as the green ones. Now, you can see that, for example, here in the middle, there was a green dot here. And apparently, this one confuses the segmentation to say that there is actually some green dots within this area. And then you have a fuzzy area here where it's not really clear what is what. And the classifier does what it can from it. Now, if we want to make a better segmenter, then we need to add the number of neighbors. So if we now change it to 4 neighbors, you can see that the result is, I should change the colors here actually, but you can see that the colors are much more well segmented here. You have a nice boundary line, except here is a little confusion, but otherwise it's pretty fine. And we could even go one step further, saying we have 10 nearest neighbors or something to make a more robust segmentation. Another way is to do linear regression. So that's a kind of a curve fitting where you relate your observed data with some response value. And it's a simple method. It's usually often easy to interpret, fast to compute. And if we look at a simple example, then we have an X array with 0, 1, 2, 3, and we have a Y array with 10, 20, 30, 40. And if we plot it, we get a straight line like this. And if we would now do plot the regression line, it would actually fit pretty nicely through these points. So far, so good. Now, if you want to put it into images and maybe add some more data points, then we have to think a little bit differently. But now I'm just first trying. What happens if we put different values in this model? And if we put x equal to minus 100, then the regression model gives us minus 990. And looking at the parameters that we fit, you can see that the slope is 10 and the intercept is 10. And then with the slope 10, you have 100 times 10, that gives you a minus 1000 plus 1, and then you get this value. So that's pretty straightforward. Now, looking at this blob example, now we only have 2 blobs that we want to do a regression on. We have a cluster of blobs, a cluster of points here, and we have a cluster of points here. And we get a group ID 0 and 1 for each point. And this now we want to put into the regression model. So what the regression model is fitting to is these positions versus the values that we want to see. Let's run it. We get some slope and in X and Y and an offset. What does this tell us? So let's look at the testing points. We have here X and Y positions, and we run the, a prediction based on this model where you can see we have the training. Oops. Hey, so sometimes it works, sometimes it doesn't. Now it has forgotten even. Let's see. Now I only have a normal pointer. I don't know why. Okay, it doesn't work. So we can see we have the training data, and if we run this model that we fitted, then we get a continuous gradient through the data. And that doesn't really help us to do some kind of decision. But if we put the threshold at 0, then you would actually see that the regression line really nicely puts a distinction between the group of the dark ones versus the group of the yellow ones. And that is how you can use the regression model, for example, for separating different classes. Another way to work with is to use decision trees. And well, in computer science, a tree doesn't look like a tree out in nature, like the one you can see here, but it's actually turned upside down. So you could say more or less that it's some kind of root system instead. But the idea is you have a tree where you make decisions in each node that if something is true, it goes to the right. If something is false, it goes to the left. And then you can build up trees like this. And an example we have here, a tree classifier where we have input data 0, 1, 2, 3, and that should be matched with 0, 1, 0, 1, which is more or less a nonlinear sequence on these points. What the tree does is to split it down into tree fitting, gives you a tree that looks like this. And what it tells you, if you look at the details, is first of all, you have 4 samples at this node, and you have 2 values going in this direction, and no, you have 2 values of category 1 and 2 values of category 2. The splitting is now that we split at 0.5, and you can't land in this group here where you have 1 out of category, the first category, so that's the 0 actually, and none otherwise. And you only have 1 sample in this leaf. The other group, you have 3 samples, and in this one you have still a 0 and 2 1s. And then it does another splitting at 1.5, so that would be here, and it gives us a new leaf. And this time you have 1 in category, so we have 1, 1, and no zeros. And there is only 1 sample in here. You still have the next one where you have 2 samples. You have a 1 and a 0 in this data block here. And when it splits up, you have then a 0 and a 1. So this is how the tree is built up. Then you have as some kind of value of goodness is the so-called Gini index, which is 0 if you have all items the same. And then it degrades if you have more and more values in the different values within the group. And what is based on is the probability of each class. And this can be done on the blob data, for example, which I need to execute. And here it looks, let's see if I can go up. I can't. Yeah. Anyway, we have the blob data. It's just a repeat again. And if we train it, it looks a bit differently now, the tree. It's still quite unbalanced. Ideally, for having the quickest search in the tree, you want to have it very balanced. So you have the same number of branches on each side. But if you have nonlinear data, it could be that it gets a bit unbalanced. Again, you can look at the same kind of splitting. I'm not going into the details here now. And the result from this tree classifier is you have something like this. It's splitted up the data. Maybe it doesn't make sense to you. One thing is you can see that this bar here is probably dominated by these points you have here in this group. This bar here is to fit in this dot, and then you had some yellow in between, and that is why you get this kind of test points in when you scan this image, scan the data. A single tree may be good to work with, but why not add more trees to increase the power of this classifier? And what you do is you're creating multiple trees on different conditions. And then you take the response out of the majority answer from all these trees. So again, we have three overlapping blobs. They are pretty noisy. You can see that there is a very much overlap between the green and the purple one. And the yellow one is not so much overlapping. So that would probably be easier to handle. And if we look at, so it's trained, we have a forest based on 5 trees, and we try to fit 5 different trees in this model. And what it looks like, one tree is much more complicated. We have so much overlap that the tree needs to take care of all combinations that it comes across. And when you have a tree looking like this, it's not so easy more to understand what it's actually doing. But the fitting models, they're optimizing to get the best result out of it based on the given training data. So what you can look at, you have now these 2 classes overlapping, and the total response of the whole forest is something like this, where you can see, okay, the yellow makes pretty much sense. The green ones kind of make sense. This little yellow slab here is probably because of this point. And then if you look at the separate trees, you can see that this one almost looks like the whole tree segmentation, but this one looks very much different. So it's looking at a different subsection of the training data. And now I'm switching to a tool how you can do your analysis, and that is using pipelines. And a pipeline is a way of programming to make it more easy to see the workflow. And it's supported. Let's return to the blobs. Let's create them again. So, and what it does is essentially you have different work items, and in many image processing tasks, you have a chain of operations that you want to do. Sometimes you have a second branch of something that happens in parallel and you need to fit in afterwards, but mostly you have a pretty straight sequence of operations. Now in scikit-learn, there is a kind of a pipeline engine which supports predefined operations. Like, for example, here, I'm working with an item called robust scaler. So it normalizes the data to get rid of the impact of, for example, outliers. And running this, we can see each of the steps. We have some input data. I actually have to check what's, so that I think that was the blob data. So now it's some kind of normalization that is done. And we can see also the histograms that are resulting from this. In the beginning, you can see that we had pretty wide spread. Some of the data was scaled from -10 till 10, no, -10 to 2, 3. The other one was scaled in this way. So you have a little bit negative and a lot of positive. And the last one was just a few data points. So I think it's just 1, 2, 3 or something like that. After normalization, you have everything centered around 0, more or less. And that makes it also easier to run these segmentation algorithms afterwards. Now we want to add another type task to the pipeline, and the pipeline, as we have done it, is actually, I think I should sit down and do this instead. Now we have defined our pipeline as a list of different operations. You have the quantile transformer, and you have the normalization using the robust scalar. And then we can do some fitting, and it executes these tasks. Then you can see also the output again, that it's reshaping the data in different ways. And now we want to add also, for example, polynomial features. Then you add all the exponents, so x to the power 1, 2, and then you may have some cross parameters as well. And that is what's added here. So if we look at this, now we have polynomial features, and you see you add actually the amount of data you have in your data pipeline. And that will be used later in the segmentation. Let's see, yeah, next page. So now we want to do a classification using this pipeline, and we want to see what happens when we classify the digits from 0 to 9, or I think we actually take less. Oops. So yeah, we have images of numbers 0 to 9. The images are 8 by 8 pixels, really small. We have 50 samples, and we want to look at them. So first, let's load the digits and look at the information in them. Now it's just looking at the shape. And next step, we do some flattening to adjust the gray levels. And no, flattening is making a one-dimensional vector out of the data. And the next one is normalizing the data. And then we run this pipeline and see what happens. So you have the input is like this. The flatten gives me a lot of lines. And on the y-axis, you have the gray levels, I believe. And on this axis, you have the vectors of the pixels. Then we normalize, everything shrinks down around 0. And let's see if I can get this one up. No, I can't. You would see a lot of histograms here. I think I should maybe even switch now from the presentation mode. Now you see it better. No, that was wrong. Like this. Yeah, a little bit larger. So now let's add a classifier to this data. So our program just means that we add more and more items to this pipeline object. And that makes it possible to, for example, just create these lists of items, and then you can easily switch your segmentation procedure on the fly. So that is the purpose here. So this, you have the program is in the form of a list instead of some code. That makes it flexible if you want to test different methods. So now we run it. We did the nearest neighbor, and let's test what the performance is. And what you get now is really nice. We have 100% accuracy. Is that good? So let's look at the confusion matrix. And what it gives us is very nicely. Oh, we got 7 zeros, we got 5 ones, and so on. Looks great. Let's continue and see what the output is of this classifier. We have different precision, recall, everything looks really great. So we got the perfect algorithm, didn't we? Maybe. Let's try again. This time we try with new data. So we only used a part of these numbers in the MNIST data set. Maybe they were not the right ones or something. So now I create a new image that should correspond to a 9. It looks like this. And the prediction now from this image, this classifier says it is actually a 7. So that means it wasn't really good what we did. So the question is what we did actually. And here is the question, what happened. I trained and I tested on the very same data. And with the k nearest neighbor, you will definitely get exactly the same answer. And what you need to do is actually you have to have a training and a validation data set. And then finally, to evaluate how good you are, you need even a test data set. Then you are doing it the right way. So nah, it wasn't really a good way to go on. There is also, so that this image comes from this page here. So let's add regression instead of k nearest neighbor. And the regression type is, let's add a little bit. Now we load some digits, and this time we are working with 50 images and labels for the training, and we work with 400 images for validation to see how good this actually is. And now we have split up the data. We loaded the digits, we split it. We have the 50 training data and the 450 validation data. Now we run a k neighbors regression. You can read more about that one here and see what happens. The pipeline is now changed. And now we can see that we have run the regression and we get some results. And we want to now check how good is the quality. And now if we want to check the performance, we can't use the ROC curve. We can't also use the precision and recall. So we need to use something else. And typically what would be used is mean squared error or mean absolute error. And looking at those, you can see some performance. If we look at the predictions based on the training data only, we have very good fit. We have exactly 0 goes to 0, and yeah, each number goes to what it's supposed to. Now, if we try it instead on the validation data, we see that there is a good hit sometimes, but we also have some misclassifications in this block. And we can improve this by increasing the neighbor count. So in our scalar, in our pipeline here, now we change to 2 nearest neighbors and see what happens. It runs again, and now we can see, no, it didn't do much better, but now actually the predictions of the training data got a bit confused. And here you have to play with different settings. Maybe we should try something else, 5 neighbors, and see what happens. Yeah, it's not, it seems like the k nearest neighbors regression is not the right method to do this kind of segmentation. Now we go to an image classification of a little larger case. We want to look at the cells, the mitochondria. And here we have a very difficult case because there are the mitochondria and there are some walls here between and a lot of other items that have more or less the same grade level. And for the human eye, it's quite easy to see them, but it's not ideal condition that we have all this almost same contrast case. And also the signal to noise ratio could also be better. And I think we tried it last week already. Setting a single threshold will not give us very good results. So let's try different methods to segment these mitochondria. So we can use decision trees, we can use random forest, linear regression, nearest neighbor. And in the end, I'm also going to show you how you can use deep learning to try to solve this problem. And first, we need to read the data. And it looks like this. We have the image as it was, and we have a mask image that tells us where we want to expect these items. And let's go on. We created some training data, and we create a validation mask. So essentially what we did is splitting the image into two parts. The left part is used for training and the right part is for validation. So let's see what a regression tree is doing. So now we build up, we flatten the image, we do some robust scaling and start with the decision tree. This is very hard to interpret what it's actually doing, but you can see that the values are reshaped, at least in the scaling and the flattening. And now let's see what the output is. We have the training image, the training mask, and the prediction is more or less finding everything with the same gray level. Looking at the full image, you can also see that, again, it does actually finding the same kind of information, but still it's not the right information. So we need a different method. So let's try with regression tree with position information. So now we add something more. We do some splitting and let's see what happens. Oh, okay. Let's look at the tree. This is a huge tree. Yeah, it's really not meant to be showed in all its detail. I actually forgot to reduce this one in the same way as I did before. But looking at the information we have now, we have the mitochondria training data, we have X and Y, no, Y and X coordinates, and it's flattened. And then we can see what the different steps are producing here. Let's see what the performance is doing here. In this case, the prediction mask is kind of finding what we want to. So it helps a little bit to have this position information. But if we now try to see what happens when you work on the prediction mask, no, on the validation image, you see that it's within the training data, it does pretty good. But otherwise, it's not really fulfilling the information as it was supposed to. And what it's more or less doing is it's stretching what it sees here on the edge, stretching it out in the validation mask. So this wasn't also a good way to do it. Let's continue. Now we have combined k-means and random forest. So now we're getting really wild. And see what happens to it. It needs to work a little bit first. So we still have the same input information. We add the k-means to get some first splitting, and then we let the random forest run on that. And you see already that it's categorized a little bit better. But how is the performance of this? Now, in the training mask, training image, it does much better than before. So we have done an improvement. But what happens now? In the full image, it is not really aware. It's so hard trained on the training data, but it doesn't generalize into the rest of the image. So this wasn't a good one either, because we already know what the training is. We want to know what's the good segmentation out in the validation. Then we can try on doing different things. We can add some polynomial features instead of the k-means and still do the random forest. And this also needs to run a little while. And we get, again, a nice split. And I actually would like to continue, if you don't mind, and then we go for break afterwards. So how does this work? And we can see again, it gets a nice prediction in the training mask, but again, we have the problem that it only stretches out at the contact point and nothing else. So this was, it goes a little bit into the validation part. So the line, I think, is about here. So it does some realistic prediction, but the rest, if there is no connection between the validation mask and the training mask, there is nothing. And we can continue adding more and more strange features. We can add maybe some smoothing with Gaussians of different types and run that pipeline. So this is more or less just testing in which way you can add more features that help you to make the right classification. And this one looks also pretty decent. And now it starts actually to be able to at least indicate the grains and the different mitochondria in the validation mask. So this starts looking like something. And now I had a combination of different filters. So we added weighted neighborhood information. And with that, we could improve the quality. And we can also work with direct neighborhoods. So we just look at the neighborhood pixels as they are. So we shift ±1 pixel. And this requires some functions to do. And let's run the fitting. Now you can see essentially the same image multiple times and see what it gives us. And that was no good idea. So it was better to actually filter the images, getting weighted information than just shift around the pixels. And I actually skipped the linear regression. It's about optimizing which filter we should use. And I'm skipping on to looking at the deep learning, or maybe looking first at the summary that you can create different pipelines, and some of them perform good, some don't. And we have to see, you have to select the right combination. Maybe it, after so many attempts, I would actually say, this is not the way to work. So then you have to find another way. Some cases, it could be relevant to use these workflows using the trees. Otherwise, they wouldn't have been developed. But what is another option when you have tricky data? I'm not saying you should use it directly, but you can use deep learning. And a very popular design of deep learning is to use convolutional network, which is based on the output of very many convolutions of the same image and also downscaling. And then when you do convolutions and then you do downscaling, this is a red arrow, then you do more convolutions and connect with weights that are fed forward. And you do that a couple of levels. You can also feed forward the information directly from here. And when you come down here, you do upscaling again. And in the end, you combine a lot of information to get the prediction of your image. That was unit in 1 minute. Very intense. If you want to learn more about it, you have to read the related papers. There is, for example, here is a paper that tells how the structure works. Here we try to build now this kind of network structure that you saw here, that we have different layers, you have downscalings, and all this can be done using Keras, which is an programming interface for building neural networks. And what we do is we're doing a couple of convolutions, we do downscaling, do convolutions again downscaling, and then at some point we do upscaling, and everything is built into a model like this. So this is called small UNet. And it takes the input with the image like this, and the output comes from layer 17. And each layer here is connected with the previous one. So let's just run this. We get a summary of the network describing the technical details, how many parameters we have to tune. And you can see there are quite many parameters that are tuned here. And looking at the schematic of it, you can see what we have built is actually a structure, and now it's actually rotated. But you see the structure that we have some convolutions, we have downscaling, convolutions, downscaling, then we are in the bottom, and then we do upscaling and going up again to the image, and you have some cross connections here too. So this is how you can build a simple unit yourself. Now we want to train this net, and we use the same image again with the mitochondria, but deep learning is a rather time-consuming method, so we reduce the data size a little bit to make it easier to handle. So let's look at what I did. Instead of taking the whole left side of the image, I now only use a fraction of it, it's about half. And then we use this part here as validation image. And looking at the untrained model, so this is actually, the unit model has some default kernels in as it's set up, and we can see what it does. And we have the training image, and we have the mask, ground truth, and this is what it predicts. And the output of the network is actually probabilities or likelihoods that the pixel belongs to the class that you are asking for. And we actually wanted a high probability for these regions and low probability for these regions. So it's actually flipped everything. But now it wasn't trained. So now we want to train it. And an important thing is that we are not doing it the correct way. We maybe didn't have the best function for doing the training, and we can also change the learning rate. But the most important comment is that the training and validation data should not come from the same image, and not not from the same sample, and also not from the same measurement. So now we have the same specimen we are looking at. Ideally, you should have a lot of images of different specimens and select a part of them for the training and part of them for the validation. But we don't have that luxury in this case. So this is what we have. We are using some training conditions, using the loss function, which is mean absolute error. We use an optimizer called stochastic gradient, which is quite a good one. It's more robust than, for example, it gives better results than the so-called Adam optimizer. So we can try with that. We will train during 8 iterations. And the metric we want to check on is the binary accuracy. So if you put the prediction output on the mask, we can see how many are correct. And also mean absolute error. And it's not absolute. So that's the correct one. And we also use the dice score, which is this function based on true positives and false positives, false negatives. And it's very popular to use as a metric. But right now, we are not using it. So let's train this model. We have already designed it, and let's compile. and run it. Yeah, get some error messages here. The new Apple computers don't really like TensorFlow yet. So I had some struggle of setting it up. But anyway, it does actually run, and you can see here that we have some mean absolute error and in training and validation data. And we also have classification accuracy. Somehow, I can't see why, but it looks like these two curves. Do you know, actually, it confused me that the validation data has a lower error than the training data. Yeah, it happens sometimes, especially in the beginning, it's quite far away. Okay, yeah. Okay, okay. But anyway, you can see that there are two curves and they are actually behaving more or less the same on both training and validation. And the output we get from this is at least setting the gray levels right, or the probabilities right. So we have here higher probability for the mitochondria and lower probability for the surroundings. It's still not really convincing, but it's better than the untrained model. And then we can, then I get, not that one again. Let's hope it works. We get only some kind of warnings. Let's hope it worked. I don't think so. No, it didn't work. As I said, I had some problems setting it up on this computer. But ideally, what you should see here, if it worked, is an improvement. But yeah, now it didn't work. Demonstration effect. So now we have also looked at different ways of working with supervised segmentation. And that requires that you have on one side training data where you have the input and the expected output. And for that, we could use K nearest neighbor, for example, or we can also use, as I showed you now, deep learning. And we looked at also pipelines as a flexible way of creating new analysis workflows. Instead of writing the source code in Python, you can just produce lists which you can read in from files easily and change on the fly. So that was today's lecture. And with that, I'm saying, well, it actually told me that break is over, but now it's break time. So thank you for today.